So there is an exact mathematical number of theories that a human brain can physically understand.
Right.
And it's a 1 followed by 30,000 zeros.
Yeah, which is just, it's massive.
It is. I mean, it sounds like infinity to me, but it's not. It's actually a hard mathematical limit.
Exactly.
So today, we are doing a deep dive into a stack of theories that ask this really terrifying question. What happens when we reach that limit? I want to welcome you, the listener, to the show today as we explore this.
What's fascinating here is the paradox sitting right at the center of this material. Because, if you look at the fundamental theorems of mathematics, they seem to prove, like, without a doubt, that we can never build a perfect system to know everything.
Right, because the universe is just too complex, right?
Exactly. But the sources we're looking at today argue the exact opposite. They suggest that those mathematical limits, well, they don't actually matter for the reality we live in.
Huh.
Yeah, and that a unified, perfectly optimized understanding of reality is, against all odds, entirely within our reach.
Which is just wild to think about. I mean, if you are the kind of person who constantly wants to learn more, who is always chasing the next concept, this whole idea of practical omniscience, it sounds like pure science fiction.
It really does.
But let's start with that massive number, just to set the scale of what we are trying to understand. So the sources calculate the total space of human understandable theories.
Yeah, they set a very specific parameter for this.
Right. They say, assume a theory uses an alphabet of about 1,000 characters. So, math, symbols, logic, regular language, and it has a maximum length of about 10,000 tokens.
Essentially, picture a very dense, incredibly complex scientific paper.
Yeah, exactly. And the total number of possible theories you could construct with those exact parameters is 10 to the power of 30,000.
Which is just an astronomically large number.
But the crucial word there is finite. Like, there is a hard ceiling to the space of theories that a human being could ever meaningfully grasp.
And that really brings us to the real bottleneck here.
Yeah.
Because it isn't the universe that's the problem. It's our hardware.
Our brains.
Right. When you compare that massive theory space to human cognitive architecture, the contrast is kind of jarring.
Yeah.
I mean, on a biological level, the human neocortex is incredibly impressive. You have roughly 20 billion neurons and, 200 trillion synapses firing away.
Right.
But your active symbolic bandwidth, the part of your brain that actually processes complex theories, math, logic, it's tiny.
Okay, let's unpack this, because 20 billion neurons sounds like a massive amount of processing power. Why is our active bandwidth so small?
It's because of something called sparse activation. Essentially, only about 1% of your neurons are actively firing at any given time.
Wait, really? Only 1%?
Yeah. If they all fired at once, your brain would literally overheat. It would consume more energy than your body could physically provide.
Oh, wow. So it's an evolutionary energy-saving measure.
Exactly. So when we look at your working memory, you can really only hold about 4 to 7 chunks of information at once.
Huh.
In terms of raw data, your active symbolic bandwidth is maybe 100 to 1,000 bits at a time.
That's nothing.
Right. Your long-term storage is massive, sure, but it is incredibly slow to access and write to.
So to put a visual on this, it's like, imagine you're trying to observe an entire vast, bustling city, but you are only allowed to look through a little plastic drinking straw.
Oh, that's a good way to put it.
Right. Like the whole city is there. That's the universe.
Right.
But your hardware, the straw, limits you to seeing one tiny isolated detail at a time.
Exactly.
So if a superintelligent AI discovers a perfectly accurate theory of the universe, but, understanding it requires holding a million variables in your head at once, it's completely useless to us.
Completely.
It's like trying to download a terabyte of data through a 1990s dial-up modem. It just won't fit through the straw.
That is exactly the issue. The data exists, the theory is objectively true, but our hardware physically cannot receive it.
Right.
And this is why the sources explicitly state that raw scientific discovery just isn't enough on its own. Representation design and language are, well, they're just as critical as the discovery itself.
Meaning we have to compress the data before we pass it through the straw.
Exactly that.
Yeah.
To squeeze these massive universe-explaining theories into our narrow cognitive bottlenecks, we have to compress them using specialized languages.
Okay, like what kind of languages?
Well, the sources mention developing languages that map cleanly to human cognition. Things like Montague grammar, which basically attempts to map natural language directly into formal mathematical logic.
Oh, so there is zero ambiguity.
Right. Or Lojban, which is an artificial language constructed specifically to remove the messiness of human grammar.
Wow.
Yeah, so curriculum design matters just as much as a lab experiment because it dictates how efficiently we pack that data into your brain.
Hold on, though. I have to ask. If our brains are such a tight bottleneck and there are, 10 to the 30,000 possible simple theories out there, why do we even need to rely on our brains to sort through it?
What do you mean?
Well, why don't we just build, like, Dyson sphere-sized supercomputers?
Ah, I see.
Right? We could harvest the energy of an entire star, build billions of quantum computers, and just brute force our way through every single combination of those theories until the computer hands us the best ones.
It's a fun idea, but because even with all the energy of a star, brute force is totally dead.
Seriously?
Yeah. Let's imagine you actually build that theoretical mega computer. Let's say it's capable of doing 10 to the power of 50 operations per second.
Yeah.
Even with billions of quantum computers and star-scale energy, you cannot brute force all theories or all programs or all proofs.
But I refuse to believe we couldn't brute force it. I mean, star-scale energy has to count for something. You're powering a computer with a sun?
I know, it sounds like it should be enough, but you are running into the wall of combinatorial explosion.
Okay, explain that.
Think of it like a combination lock. A lock with 3 dials is easy to crack.
Sure.
Add a 4th dial, it gets harder. By the time you have a lock with 1,000 dials, the number of possible combinations doesn't just add up. It multiplies exponentially.
Ah.
So when you try to search through these massive theory spaces, the number of candidates explodes so fast that even a computer doing 10 to the 50 operations per second is essentially standing still.
Wow. So the math simply outpaces the physics.
By a landslide. The sources point out that many of these problems are what computer scientists call NP-hard.
NP-hard.
Think of an NP-hard problem like the ultimate traveling salesman puzzle.
Okay.
Finding the single most efficient route between 100 different cities isn't just difficult. The number of possible routes explodes so fast that even a computer the size of Jupiter couldn't check every single path before the heat death of the universe.
That is mind-bending.
Right. And contrary to popular belief, quantum computers don't just instantly solve NP-hard problems.
They don't. I feel like that's always how they're talked about.
It's a huge misconception. They only provide a quadratic speed-up for unstructured searches, which honestly barely puts a dent in a combinatorial explosion.
Okay, so physical brute force is out.
It's out.
But the sources also bring up the heavy hitters of mathematics to say that even our logic has hard limits. The scary theorems.
Yes, the impossibility theorems. We are talking about the foundations of computer science laid by Gödel, Turing, Rice, and Kolmogorov.
The absolute legends.
Truly, and these mathematical giants proved definitively that there are hard walls to computation. Take Alan Turing, for example.
Okay.
He proved what's known as the halting problem. He showed that it is mathematically impossible to write a single perfect algorithm that can look at every other computer program and determine if it will eventually finish running, or if it will just get stuck in an infinite loop forever.
You just can't build a perfect judge.
Exactly.
And Gödel did something similar for math itself, right?
He did. Gödel's incompleteness theorem proved that no single formal system can prove all mathematical truths. Essentially, math cannot prove all of math.
That's so trippy.
Yeah. And then you have Kolmogorov, who showed there is no single optimal compressor for all strings of data.
Wait a second.
Yeah.
If math itself, Turing and Gödel prohibits a perfect algorithm, and the physical limits of the universe prohibit us from just brute forcing the answer with a Jupiter-sized computer, hasn't our deep dive just hit a brick wall?
How so?
Well, if we can't compute it and we can't prove it perfectly, isn't omniscience mathematically dead? Like, shouldn't we just pack it up?
And that is the exact trap most people fall into.
Really?
Yeah, they see those theorems and they just give up. But here is the most crucial revelation in the text. Those impossibility theorems apply to all possible strings of data,
Okay.
all possible programs, all possible mathematical statements. They apply to completely random adversarial data,
Oh.
right? But the universe you and I live in is not random noise.
It has rules.
Yeah.
It's structured.
Yes. If we connect this to the bigger picture, the real world is incredibly low entropy. It is redundant. It is pattern-rich.
Because gravity works the same way here as it does on Mars.
Exactly. A water molecule operates by the exact same rules in your glass as it does inside a comet a million miles away.
Right.
The universe is highly compressible because of these repeating patterns.
Hmm.
The theorems from Turing and Gödel say we cannot have a single magical algorithm that solves everything perfectly.
But we don't live in everything.
Exactly. We live in a highly specific, highly structured universe.
Oh, I see. So we don't need the magic algorithm that works on random garbage data. We only need algorithms that work on the stuff that actually exists.
You've hit on the absolute core of the argument. We just need a finite toolbox of algorithms that covers all the decidable problems humans actually care about.
Wow.
We need a finite set of formal systems that collectively prove all useful mathematics, for building bridges and launching rockets. The mathematical limits simply do not bind in the domain we actually care about.
And the mechanism the text identifies for building this specific finite toolbox is neural networks.
Yes.
Which, makes sense because neural networks are fundamentally deterministic algorithms that learn other algorithms.
That's the secret. A neural network can't solve Turing's halting problem. It can't automate all math perfectly. But it can learn heuristics.
Let's define heuristics for a second, actually, because that's a term that gets thrown around a lot.
Good idea. A heuristic is essentially an educated guess that is good enough for the real world.
Okay.
We don't need absolute mathematical proof that a bridge will stand up to every possible, impossible scenario in the multiverse, right?
Right, that would be a waste of time.
We just need a heuristic that proves it will stand up to Earth's gravity, wind, and traffic. And neural networks are incredibly good at learning these heuristics.
Because they learn search strategies, representations, and compression.
Exactly. They escape the mathematical limits by approximating the exact tools we need within the structured bounds of our physical universe.
Which sets up this incredible explosive loop mentioned in the sources.
The recursive loop.
Right. It goes like this.
Yeah.
We use our current compute power to make a better AI.
Yeah.
Then that better AI discovers better algorithms and heuristics, and those better algorithms make the computer's processing power even more effective.
Right.
And then that more effective compute makes an even better AI. It just spirals upward, totally feeding itself.
And what's vital to understand here is that no theorem in mathematics forbids this loop of recursive self-improvement.
None of them.
Nope. Unbounded improvement in structure discovery, in data compression, in language design, none of that is blocked by Gödel or Turing.
So if algorithms are constantly improving themselves, we have to look at what happens when hardware catches up to this explosive loop.
Exactly.
Because the sources don't just look at raw hardware, they measure something called effective compute.
Yes, the real measure of capability. So think of effective compute like a car. The hardware is the engine, how much raw horsepower you have. But the algorithm is the transmission and the aerodynamics. It's how efficiently you get that power to the wheels and cut through the air.
That makes perfect sense.
Right, so if you only upgrade the engine, you go faster, sure, but if you upgrade the engine and design a perfectly efficient transmission at the same time, your speed doesn't just double, it explodes.
Historically, hardware improves exponentially.
Yeah.
And algorithms improve exponentially. So when you multiply them together, you get super exponential growth.
And now, add entirely new physical architectures to that engine.
Right, we're not just talking about shrinking traditional silicon chips anymore.
No, the sources list completely new ways of processing data. Things like photonic computing, which uses light instead of electricity to move information.
Great.
Stochastic computing, which computes using probabilities instead of absolute certainties, mimicking how the real messy world operates.
Oh, wow.
And ternary logic, which moves beyond just zeros and ones to zeros, ones, and twos. It massively increases data density.
Okay, here's where it gets really interesting, though.
Yeah.
Where does quantum computing fit into this? Because earlier we said it couldn't solve the traveling salesman puzzle.
Right, and the sources are very careful to say quantum computing isn't a magic wand. It won't solve global NP hard problems.
Right.
But what it is an insane multiplier for very specific, very necessary bottlenecks.
Like what?
It radically accelerates linear algebra. It accelerates search in structured databases. It accelerates symbolic regression, which is the process of an AI looking at a bunch of raw data and finding the exact mathematical equation that explains it.
So when you combine super exponential algorithmic growth with these new, radically different hardware multipliers,
Right.
you get runaway structure discovery,
Right,
runaway compression, runaway theory formation.
Yep.
Wait, earlier we talked about how human working memory is effectively a plastic drinking straw.
We did.
If this AI compute loop keeps accelerating to infinity, aren't we just going to get left behind entirely? Doesn't the science just completely outgrow our biology?
If the goal was infinite complexity,
Okay.
But the text introduces this concept of practical saturation, or the 99.9% threshold. Think about a television screen.
The 2010 vision analogy.
Right. Once a display passes the resolution of 2010 human vision, engineers can pack 1,000,000 more pixels into that screen, and it absolutely does not matter to you.
Because I can't see the difference anyway.
Exactly. The human eye literally cannot perceive the difference. The just noticeable difference, or JND, has been surpassed.
Right.
Further improvement exists purely in the realm of physics, but it is entirely irrelevant to human experience.
So what does this all mean?
Well,
It means this saturation point applies to everything you experience as a learner, right?
It's-
It's not just about TV screens or audio frequencies.
exactly.
Think about education. Once an AI optimizes a learning curriculum's speed and delivery beyond the natural noise and distraction of your day-to-day life, making the curriculum any faster doesn't actually help you learn better.
Right, because your brain physically can't absorb it any quicker.
Or think about medicine. Once a drug's efficacy exceeds the natural biological variability of the human body, any further microscopic improvement in the lab is meaningless to your recovery.
Right.
From your perspective, that curriculum or that drug is just perfect.
The domain has saturated, the utility metric has hit the human limit. And the sources argue that this TV beyond 2010 vision moment is coming for all domains of knowledge.
All of them.
Theories, languages, algorithms, all hitting that ceiling where they are perfectly optimized to fit precisely through the straw of our biology.
Which paints the final picture of what we are actually moving toward.
Yeah, we are moving toward a universe where you possess infinite knowledge.
Yeah, as we established, your brain can't hold it and a Jupiter-sized computer can't find it.
What we're moving toward is practical omniscience.
Practical omniscience, I love that term.
It's the end state of that super exponential growth. The sources estimate a near future with 10 to the power of 13 times more effective compute. And that level of power gives us a finite set of formal systems that prove all useful math. It gives us a finite set of compressors optimal for all real-world data. We get a unified, compact, human-usable theory of everything.
We get optimal models for prediction, optimal algorithms for reasoning.
Everything that can matter to humans, every theory, every representation, every curriculum, perfectly compressed, unified, optimized, and made completely accessible.
It respects the physical limits of our brains and the mathematical limits of the universe, but it perfectly fills the space between them.
Exactly. And nothing in computability theory forbids it.
It's just an incredible reframing. We aren't locked out of understanding the universe. We just need the universe translated and compressed into our native format.
Spot on.
But that actually leaves me with a thought I want you, the listener, to mull over before we wrap up today.
Let's hear it.
We talked earlier about how the sources champion creating optimal languages for thought, things like Montague grammar or Lodgebon, to bypass our human cognitive bottlenecks and compress these massive theories into our 4 to 7 chunks of working memory.
Right.
If our recursively self-improving AI eventually designs the mathematically perfect, highly compressed language for human cognition, will our natural, messy languages like English or Spanish eventually become completely obsolete?
Oh, wow.
Right? Will we be forced to actually change how we speak and think just to interact with the new, perfect universe?
It is a wild thought.
It's something to think about. Thanks for joining us on this deep dive.